Okay, are you all ready for the class today? Okay, I think I'm going to finish chapter 10 today, okay? And the two topic we need to talk about, this heteroscedasticity in chapter 10 is the detection and the remedy. Okay, first of all, that's all, have the data either in eViews or in Gradle, okay? With the data set, guess 10. We'll have that ready? Okay, I'll show the eViews first. Okay, and let's see. Now, I have already this model with y variable as PCOM and two x variables with price and REG. So this is the petroleum consumption. I think we did this one last week. And the price is about the price of gasoline. And the REG is the registration of automobile. Okay? So we use this model, and we like to check. Okay, this is the estimation using OLS methods. Okay, then we like to check whether this model has the problem with heteroscedasticity. Okay, so if you have the book, and the book shows us that there's two popular ways to do it. Okay, one is called Brooch-Bacon test. Usually, for short, we just call it BP test. And the other one is called White. Okay, and I like to show how to do this two test in using eViews. Okay, you need to have this model output first. Then let's see, view, and see the let me see, is the residual diagnostic. Okay, and find the subfunction of heteroscedasticity test. You'll see that? And there are several you can choose from. Okay, and we're going to talk about is the first one called BP test, and the second, White. Okay, this is all introduced, and the most popular way. And the idea for these two tests, okay, I'm saying, express some logic behind these two approach, okay? And the first one, BP test, is look at, if you have the textbook, okay? First of all, that looking at the relationship with the model's residual, square of the residual, okay? The residual, okay, with the original x1 and the x2, epsilon, something like this one. Okay, we wanted to see the residual from the output and see whether they still have relationship with the original x1 and x2. Because according to the OLS model, the residual shouldn't have any relationship with x1 and x2. Okay? So after we do this regressions, then this is the residual. So if I use the residual as a dependent variable, then original x1 and x2 as an x variables. And then if there's no heteroscedasticity problems, then what happened to all this coefficient? If there's no relationship with the residual and original x1 and x2, the coefficient should be equal to 0. So my null hypothesis is 0, okay? Then alternative hypothesis will be at least 1 alpha j not equal to 0. So as long as either one of them, one of the x1 or x2 related to the residuals, then there's something wrong with the relationship with these two, right? They have a relationship. Therefore, heteroscedasticity problem exists. So this is the idea of the BP test. Okay? And what's the white test? The white test say that with just x1 and x2 is not enough. Maybe the residual has some curve relationship with x1 and x2. And this is just linear relationship. Okay, since this x1 and x2 is all raised to the first power. So if we have this x1 and x2 involved with the residual is not linear, it's the curve. So we should include it. This one, not only this two, but also x1 square, x2 square, and the cross product of these two variables. So x1 times x2. So the difference of BP and the white, this is white. White say that I use this one as a y variables, but not only these two, but also these three. Okay? Then I can capture more information about the relationship of original x variables with residuals. I think this is the difference between these two. And what's the drawback for this one? If I have two variables, then what's the degrees of freedom? When we say the degrees of freedom, is always talking about the residuals degrees of freedom, which is the t-test and also the f-test degrees of freedom. Okay? And the degrees of freedom for BP here is n minus k. K means the number of x variables and constant term. So it's k minus n minus k minus 1. Then how about this one? I have 5, not only this 2, but also this. So here will be n minus 2 minus 1. But here is n minus 5 minus 1. So the more minus in the degrees from the degrees of freedom, from sample size, then the degrees of freedom become less. So this is just only 2 variables. If I have 5 variables, then here I have 5 minus 1, right? N minus 5 minus 1. If I have 5 from x1 to x5, then here I have square terms, another 5 square terms, and also how many of cross product of x1 and x5 is 5 minus times, so is 10. So here I will use n minus the original x is 5, then square term is 5, then another cross product term. So it turned out to be this one is minus 20. And here it's only minus 5. So the more original x variables, the more difference of the degrees of freedom cause for these two tests. But there's remedies for y test too. You know, since we're working with this x1, x2, x squared, something. Somebody say that instead of using the original one, I'm just using original y hat, since y hat will have the information of this two variable, right? And y hat squared. If I square it, original y squared, then I have all this original x and the square term as well as product term, cross product terms. So if I replace y hat with y hat square, then this problem solved. Therefore, white is pretty popular too. Okay? All right? All right. And usually when you see the programs, okay, you'll see that they are using this one instead of this one. Okay, using this one. We will see the output. Okay? So I'm trying BP test first. Okay? So here I'm choosing the first one. And I hit OK. So what did you see? What did you see? Look at this one. Look at this. Do you see that dependent variable is the square terms, residual square terms? So it is this one. Okay? And the variable is original 2 is this one. But the purpose is not looking at. The purpose, we can see that since we want to do the hypothesis test of this one, okay, you're looking at the second one, using observation times r squared equal to 9.885, which is a chi-square distribution with 2 degrees of freedom. This 2 means I have x1 and x2, 2. So the chi-square with 2 degrees of freedom. And what's the probability? So it means that I'm working with the test, and the test statistic is n times r squared, which distributed as a chi-square distribution with 2 degrees of freedom. Then this test, the statistic, the number is 9.85, and the p-value is 0.0073. So how do you do what is the result of this p-value according to this hypothesis testing, which is smaller than alpha level? So if you're using less than 10%, this is pretty small. Therefore, reject null hypothesis. Means at least one alpha j not equal to 0. Therefore, heteroscedasticity problem exists. Okay? You see the points? You see the points? Is that clear? Okay? So this is what we call using the BP test. We don't have to do it by ourselves, gradually, step by step. We don't have to do that. Just since there's a command on it, just hit this command. You have to know where to find this command, right? Functions, okay? And if I look at, if I'm using Y test, okay? This is the VP, right? Let me save this. I'm able to save this one? So if I save it, name it equation 1. Okay, then estimate again, and using this view, residual, again, diagnostic, heteroscedasticity, and now, this time I choose white. You all with me? Then I hit OK. Look at This is y-test. So look at the top, the title, heteroscedasticity test, white. Now, look at this output. I have two. One is x1, x2, okay? Then I have square terms plus the product terms. Did you see that? Now I have 5. Okay? Again, looking at the second column shows observation times r squared, means this one. This is our test statistic. Okay? Then I'm using white, so the degrees of freedom become 5. Therefore, did you see that? The probability of chi-square, 5. What's the probability? Even smaller. For decimal place, for 4 decimal places, still 0. So again, using y-test, it shows that heteroscedasticity problem exists. All right? This is the 2-way to detect y-test. But I think I talk about originally. Maybe you can using the graph, right? You can see the graph. If we have the variance, I mean the residual plot is looking like not random, but some pattern or some shape, okay? And this is always the first way to suspect whether we have this problem. Then the BP test and the y-test will be official scientific test, which will have some numbers on it, and we can trust with. Okay? Any problem? No? Okay, so I'm using these examples, which it also shows all this result in our textbook too. Okay? May I go on to the remedies? So far, any questions about that? Okay. Okay, let's talk about remedies. Do you all remember what's the consequence of heteroscedasticity problems exist in the model? You remember that? Okay, never mind. Let's remind it. Let's refer to our consequence. Okay, the consequence say that although there's a problem exists, but using OLS estimation is still unbiased. Okay, but you have to have this in mind that unbiased doesn't mean it's correct. The definition of unbiased means the expected value of the estimation is equal to the population parameter. In other words, what we do this here is, if we have distribution, I'll draw the diagram, okay? Okay, the coefficient estimation is T distribution, right? If it is unbiased, means the expected value of the beta we estimate, either one of the beta, will be equal to the population beta. Okay? All right? This one will be equal to this. So it will in terms of either one of the coefficient of either one of them. So if this is the first one, this is the first one. This means we estimated from sample. This is the population parameters. Okay, unbiased means the expected value of all this. What do we mean by all this? Means that if we have as many as samples, every time when we run the regressions, we do have beta 1 hat, right? Then with different samples, you will have different beta 1 hat. Understand this one? Since we have different samples, means the original data will be different, a little bit different. But all the samples are from the same population with different sample values. Therefore, we have different beta 1 hat. But if you have as many as samples and you estimate the beta 1 hat every time, then you have as many as beta 1 hat. Then the expected value of that will be equal to the population's beta 1. So your sample, this is the populations. And if the beta 1 is somewhere, let me just say that since this is a mean, right? So if I say this is some beta, if the distribution is something like this one, what's the difference between these two distributions? This one is taller, skinnier. This one is fatter, shorter. The shorter and fatter one means what? The variance is big. Skinnier, taller means the variance is smaller. So heteroscedasticity causes the problem of variance which become bigger or smaller. Either bigger or smaller. When it is bigger, means standard error is increased. If it is smaller, standard error decrease, right? If with the same beta, different degrees of freedom, that will affect the value of t-value. Agree with me? T-value is using the beta divided by the square root of the beta, right? Beta hat, right? T-value. So the standard error increase or decrease. When it is decrease, that will increase the t-value. Decrease will affect the t-value. Decrease will decrease, right? So it means that t-value become too big or too small. When t-values become too big, means the p-value is small. If t-value become bigger, that means p-value is bigger, right? So since it is not correct, so it means that we base on the p-value to reject or not reject the null hypothesis, right? So if it turn out to be too smaller, means what? T-value is too smaller means what? T-value is too smaller, p-value would big. So we easily to reject the null hypothesis. Then if t-value become too big, then too small, I'm sorry, t-value become too big, the p-value will smaller, which easily to reject the null hypothesis. So either one will influence our type 1 error. P-value is the observed type 1 error, right? Because we all compare with the alpha. Alpha is allowable type 1 error. P-value is observed, according to the data. Okay? All right? Therefore, T and F, no, F is for the whole models, right? They're all based on some standard errors. Okay, so the standard error increase or decrease means, we do have this unbiased coefficient, but standard error is not stable. Either increase or either decrease. Therefore, the hypothesis testing, the result of the hypothesis testing is unreliable. Okay? That's the problem for heteroscedasticity. Okay? So, that's the consequence for heteroscedasticity. So in order to solve the problem, okay, there are several ways to do it. Okay? And I'm going to say one most popular and easier, and you can, get it from the computers, is what we call, we have this remedies in our textbook too. We call it heteroscedasticity corrected standard error. Since we were concerned with the standard error caused by heteroscedasticity, therefore we have a methods called heteroscedasticity corrected standard errors. In other words, we are making some ways to to change or to correct the standard error. And since the estimator coefficient is still unbiased, so leave the unbiased estimator of the coefficient there, but change the standard error. So in other words, if you do this one, you'll see that two models, if you correct it and without corrected, original one is without corrected, but the one using the corrected methods, then you will see the same coefficient but different standard error, either smaller or bigger. So let's show it, okay? All right, then how do we get that output? How do we get that? Let me see. Let me do this one. Estimate, okay? I think I have the original estimated. This is the one. Oh, let me see. Oh, I'm sorry. I have to do this one. Okay, usually when I put this one, I didn't do anything, just regular, what we say, OLS, estimation using these methods. Okay, this is called OLS model. But look at some functions. I have options. Did you see that? Options. Options. Okay, look at, if I'm using estimation default, means I don't do any corrections. Okay, here you can pull it down. Then there's one called white. Did you see that? This is what we say the heteroscedasticity corrected standard error, and this is proposed by White, the same White as this one. Okay, he's White is famous statistician. We'll see many White, it's all proposed by him. Okay, so this one, if you hit the function White, then put then I will compare this one. Let me see. Did I do that? Estimate. I'm sorry. Estimate, then options, right? Then I'll choose White, right? Then I hit OK. All right, this is what I have. I like to compare this one with the original one without correction. Look at this one. Do you see that? White heteroscedasticity consistent standard error. Did you see that? Okay, this is the difference with the first one. I didn't do the correction. Okay, I'll put this. I think this one is equation. Let me put this equation 2. Do I have the equation 1? Still? I'll put this equation 2, okay? Put this one. 2, okay? And I hit OK. Let me go back to my where do I get I'm always a problem with going back to my data. Where can I get back to my data? Is here, right? Is this one? Oh, this one? Yeah, I wanted the original. Do I have that one? I don't have equation 1. This is the equation. Let me see. Let me see this output. This 2, okay? This is the same as. Yeah, okay. This is the. Oh, all right. Thank you very much. Okay, look, let's compare these 2 output, okay? You'll see that both of them have the same coefficient. Did you see that? They have the same coefficient, right? But look at standard error. It's different. The one with, this one is without correction. This one is with correction. Let's see the first, price. The one without correction is 750 something. And after the correction is bigger, right? It's 1,360 something. Okay, what else do we see? Here is all increase. Look at the second one, REG. The first one is 0.0127 something. And after the correction, it becomes to 0.03 something. And you see that with the same coefficient, but different standard deviation, standard error. In this examples, is increase, means the t value decrease, right? So look at the 2t. So look at this one. For the original one, the price and REG are all significant because the p-value is less than 10%. I'm just using the 10%. You can use 1%. You can use 5%. Either way, okay? And since 10% is allowable in business area, I don't know what's about in engineering parts, but in business area, 10% is allowable. So as long as it's less than 10%, it's okay. But now, if we correct the standard error using white, then the first one, price, the probability becomes to 0.1723. But remember, this is what? The output is always shows the 2-sided test. And what's the intuition for the price and the consumption of the gasoline, the petroleum? When price go up, then the consumption of petroleum goes down, right? So which is negative relationship. And since we expected the sign was negative, means one-sided test. And if I divide it by 2, 0.1723 becomes to less than 10%. Agree with me? Okay? But if you insist with alpha is 5%, then the price is not significant in this case. Okay? So this is this is the most easiest one, and which we can find commands from packages. And it's popular, yes.
So the wide macro is better model than the correct model?
After we do the correction, because we are all test whether there is a heteroscedasticity problems, right? And we found they do have heteroscedasticity problem. Therefore, we need to do something about it. Okay? And white is the one popular way to do it, since we have the computer packages. So it's most the easiest one. So
There's no type of specificity problem, then we don't need to do that.
well, usually, if we do this one, okay, we are not able to check the heteroscedasticity problem anymore, because by nature it already corrected. But if you use some other way to do it, okay, you need to recheck whether some other way after some other way still have heteroscedasticity problem exist. So it does not guarantee if you do something, then the problem disappear. It doesn't guarantee. But this ways, since theoretically they do the corrections for all the standard errors, so you may not have the problem. Let's check. Let's see your. Can I? From here, this is the way we already do the corrections, right? So can I do it from here to, this is the one. I can use this way to do the residual test and test the heteroscedasticity, right? But here, after I do the corrections, I'm not able to do. I need to do this one, right?
Yeah,
But I cannot do.
do it unfreeze. You cannot do it unfreeze.
Okay. So I have to.
You have to redo it.
Okay. Let's name it equal. This is equation 2, right? So this is. Let me name it. I wanted to save it. So this is equation 1, right? Okay. After that, so I turn this one off. And
Yeah.
delete. So I turn it off, turn it on,
Yeah.
and do the view again. Okay. Oh, sure. Thank you very much. Then I do the residuals. Then I see this one. Okay. And I can use Y test again. Okay. Then I do the test. What does this tell us? It seems that I still have heteroscedasticity problem exist, right? But actually it is already corrected. But it's not guaranteed, It's not guaranteed. Good, this is a good point. All right? Okay. So this is the most easiest way, and most researchers use this way. And if you see all the published article, they do this way too. Okay, it seems that this is the bottom line. It's not bottom line, it's the initial line. It's not bottom line, it's initial line to do the corrections. Okay, so usually, since heteroscedasticity exists in cross-sectional data, so usually if you work with the cross-sectional data, you need to start it with, of course, you need to check whether there's a heteroscedasticity problem. If it exists, you should correct this one as the beginning process. Okay? Although after you do this one, there's a problem exists, but it is much better than without correction. All right? Okay? Any questions? Yes, yes. You mean the original? Do I have example? Maybe we show some other data, like okay, let's see that whether we have that Woody 3. Let's try that example in chapter 3. Woody 3. Okay, I'll get that data too. All right. Let's go to the chapter 3, right? Okay, let's see. Chapter 3. Evils. And there's a Woody 3. Let's try this one. See what happened. You want to remember what variable do I have? We have the y, right? Then we have n, p, and i. Remember that? This is all the restaurant data. N is about the population near that restaurant, and n is what did I say? I is the income, median income around the neighborhood, okay? And n is the competitors, okay? The restaurant's competitors, okay? The number of competitors around this restaurant, and P is it the population? I think this is population. Well, let's see. That's in chapter 3. Let's see the example definitions. Okay, make it more precise. Okay. Chapter 3. All right, that's on page 93 in our textbook. N is competition. So it's the number of direct market competitors within 2 miles state radius of the Woody location. And P is the population, the number of people living within a 3-mile radius of the Woody's location. I is the income, the average household income of the population measured in variable P. All right? So let's see. So I'm going to run y and y variables and p and I. Open as an equation. Okay. And let's see. Okay, this one. Okay, I like to check whether there's a heteroscedasticity problem. Then I'm using BP. How is it? Look at this. Look at this one. This is using. Look at the second one, right? The p-value is 0.69 something. So it means what? When we do this is BP, right? When we do the hypothesis test, and this number is 1.45, and the p-value is 0.69 something. Therefore, we do not reject. P-value is such bigger, right? Bigger than alpha. So we do not reject this one. Therefore, this model is the one without heteroscedasticity. Hmm?
If you use the white test, is it still the same?
Yeah, yeah. It is the p-value is so high, 0.91.
Oh,
Is
so p-value
so
has to be lower than the confidence level.
alpha level is not
Oh,
significant level, is not confidence level. Significance level, confidence 1 minus alpha. Okay? Significance level, alpha. Alpha is called significance level. So both BP test and Y test, okay, shows that heteroscedasticity does not exist. We have not enough evidence to infer this one. It means that this means no heteroscedasticity. It means that this is homoscedasticity. This is heteroscedasticity. This means homoscedasticity. This is heteroscedasticity. Yeah. There's no problem with heteroscedasticity. Make sense? You know, it's good to take a note in a class, right? It's good to take note. We'll forget many things. After we understand it. So this is the good with using computer, you know, in the classroom. I like that. So, you know, laptop is so important for us nowadays. Not only students, but also, you know, everyone, for everyone. And which cell phone cannot do it. Okay? So this is this is the most popular remedies. Just directly correct the standard error. And remember that since the heteroscedasticity problem caused only the standard error instead of the coefficient. So if we still using the OL's estimation, means that we retain the coefficient with OL as estimation, but do some corrections from the standard error. Then it will help us to give a better result. Okay. All right. Then let's take 10 minutes break. Then we'll come back. Okay.